everyone. Today I will discuss to you the axially loaded bars, normal or axial strain. These are fundamental topics in engineering mechanics, especially in understanding how materials deform under forces. But first, what is an axially loaded bar? So, an axially loaded bar is a structural member subjected to forces acting along its length. These forces can either pull the bar, or what we call tension, or push the bar, or what we say compression. When this happens, the bar experiences a change in length, which we call deformation. And now let's proceed to normal strain. Normal strain, also known as an axial strain, measures how much a material deforms compared to its original length. So the formula for the normal strain or axial strain is the epsilon equals the change of length over the original length, where the change of length is equals to the final length minus the original length. This formula shows that strain is the ratio of deformation to the original length. For engineering strain, the change of length is normalized with initial length. If the bar stretches, the strain is positive. We call that tension. If the bar shortens, the strain is negative. We call that compression. Also, strain is dimensionless, no units, because it is a ratio. It is often expressed in percentage. Next, let's proceed to the high and low axial strain. In this figure, this is a high axial strain. Engineering metals and alloys will begin to permanently deform after about 1 to 3% axial strain. Thus, this would almost certainly be a permanent or plastic axial strain. While in the next figure, this is a low axial strain. This is about 10 times less than the elastic limit of typical engineering metals and alloys, and would thus qualify as reversible elastic axial strain. And now, let's proceed to the sample problems. Here is the sample problem number 1. A bar has an original length of 1 meter. After loading, its length becomes 1.002 meter. Now find the axial strain. Using the axial strain formula, where epsilon is equals to the final length minus the original length over the original length. As we can see in the given problem, the length is already given. So we just need to substitute the given in the formula. And we can get an epsilon is equals to 1.002 minus 1 divided by 1, and we can get an answer of 0.02 or 0.2% strain. And now, let's proceed to the next sample problem. A concrete column originally measures 2.4 meter. After a load is applied, its length decreases to 2.395 meter. Determine the axial strain and state whether it is a tension or compression. Using the formula in getting the axial strain, as we can see, the length is already given, just like the sample problem number 1. So we just need to substitute directly the given length. Now, epsilon is equals to 2.395 minus 2.4 divided by 2.4. And we can get an answer of negative 0.0 0.00208. Since the value is negative, the column is under compression. And that is the process in getting the axial strain. And that's all.
Good day everyone. Today I will discuss shear strain in fluid dynamics, which explains how fluids deform when forces are applied. So this is the introduction of the shear strain. So shear strain is a way to measure how a fluid changes shape. It happens when different layers of fluid move at different speeds. This concept is very important in understand how fluids behave in motion. Shear strain refers to angular deformation. This means the fluid changes shape but not volume. It commonly happens in liquids when force is applied parallel to the surface. So this is the formula of the shear strain. Gamma y represents shear strain, while the delta x is the horizontal displacement, and y is the distance between fluid layers. So let's proceed to the shear stress relationship. Shear strain is related to shear stress. T is shear stress, while the mu is viscosity, and du over dy is the velocity gradient. This shows how internal resistance of fluid affects deformation. So let's proceed to the sample problems. Problem number 1. A fluid layers has a displacement of 0.01 meter and the distance between layers is 0.02 meter. Find the shear strain. So, the formula of the shear strains, we all know that the formula of this one is delta is equal to, y, shear stress is equal to delta x over y. So, our displacement is 0.01. So, mao ni ato ibutang sa delta x. Ang sa y, which is the distance, is the 0.02 meter. So, when we divide it, 0.01 meter over 0.02 is equal to 0.5. So, wala siya unit because ma-cancel out ang meter over meter. So, let's proceed to sample number 2. Sample number 2. A fluid is confined between two parallel plates from 5 mm or millimeter apart. The top plate moves with a velocity of 2 meter per second, while the bottom plate is stationary. So, ato i-find ani kay ang velocity gradient and shear strain after 3 seconds. So ang 5 millimeter atoan ni siya i-convert into meter. So, ang 5 millimeter into meter is equal to 0.005 meter. So now, na naman tayo value sa y, we need to find the velocity gradient. So, ang formula sa velocity gradient is du over dy. So, atong du ani is 2 over sa katuang dy is equal to katuang 0.005. So, when we divide it, is equal to 400 seconds raised to the power of negative 1. So, mao na to ang value sa velocity gradient. So atong pangitaon ang delta x para makuha nato ang shear strain. So delta x is equal to v times t, velocity times t. T is the time. So ang velocity nato kay 2. Ang time nga gikan sa shear strain kay 3 seconds. So 2 times 3 is equal to 6 m. So now, kay nanamtay kuan x, delta x. So ato nang makuan ang shear strain. So ang formula sa shear strain kay y is equal to delta x over y. So ang delta x nato kay 6m dayon ang ato ang y nga katong millimeter nga atong convert into meter kay 0.005. So 6 divided by 0.005 is equal to 1,200. So this concept helps engineers design efficient machines. It allows us to predict how fluids will behave under different conditions. To summarize, shear strain measures how fluids deform. It is closely related to viscosity and shear stress. Understanding this is essential in fluid mechanics.
Good day everyone. Today I will be discussing one of the fundamental concepts in physics that plays a crucial role in understanding how materials behave under force, Hooke's law. So in this report, I will explain what Hooke's law is, its formula, the meaning of each variable, and how it applied in real-life situations. So what is Hooke's law? Emerging from Robert Hooke's 17th century explorations from elasticity and springs, Hooke's law explains the linear relationship between the spring's extension and the force applied to it. This law shows that within the specific constraints, the elastic object's extensions, such as metal spring, is directly proportional to the applied force. So which means that if you pull a spring twice as hard, it will stretch twice as much as long the spring is not damaged. The linear relationship simply means the change happens in a straight, predictable pattern. Its applications span from intricacies of mechanical watchmaking to engineering advanced suspension systems in automobiles. So Hooke's law is not just theory, it is used in real life. For example, car suspensions use springs to absorb shocks, while small springs in watches help control precise movements. The Hooke's law formula is elegantly simple as F is equals to negative K times X. So in this formula shows how force, stiffness, and displacement are related. It is easy to use but very powerful in solving many physics and engineering problems. In this equation, F denotes the force exerted. X reflects the displacement of the spring from its equilibrium, and K is the spring constant that is unique to each spring. So, force is what you apply or what the spring exerts. Displacement is how far the spring moves from its original position. And spring constant tells how stiff the spring. So the higher the spring constant, the harder to stretch. Applying Hooke's law to a practical problem demands an accurate understanding of this force direction. In simpler contexts, we often regard the extension x as one-dimensional vector, giving rise to a likewise one-dimensional resultant force vector. The negative sign in Hooke's law thus accurately points to the force direction. So, which means in most basic problems, we only consider motion in one direction, up or down, up and down, or left or right, left and right. The sign positive or negative helps us know where the force is acting, which is important when solving equations correctly. Moreover, to compute x, we must account for the spring nominal length. The total length of an extended spring equals its nominal length plus the extension. So, if the spring is compressed, the total length equals the nominal length minus the extension. So, the nominal length is also called original length or natural length. So, it is the same meaning. X is the only change, not the total length. So, always subtract the original length when solving for displacement. This comprehensive understanding of Hooke's law aids in accurately applying this principle across scientific and real-world applications. So by understanding each part of the formula and concept, we can solve problems correctly and apply Hooke's law in real-life situations like engineering design and experiments. So we have a sample problem. A spring has a natural length of 0.3 meter and a spring constant of 250 Newton per meter. When a force is applied, the total length becomes 0.42 meter. Find the force applied. So we have the given natural length of 0.3 meter. And we have a spring constant of 250 Newton per meter and a total length of 0.42 meter. So we need to determine the force applied. So applying the formula of Hooke's law, which is force is equals to K times X, we use positive because we only need to determine the magnitude. So we have a spring constant, but we don't have a displacement. But we have the original length or a natural length of 0.3 meter. So we need to apply the formula of total length is equals to natural length plus displacement. So let's substitute to get the x. So x is equals to length minus natural length. So length is 0.42 meter minus a natural length of 0.3 meter. 0.42 minus 0.3, so 0.12. And then plug in the formula, 250 Newton per meter times 0.12 meter. So cancel 250 times 0.12. So we have 30 Newton. So let's have another problem. So 2 kilogram mass is hung on a vertical spring with a K is equals to 400 Newton per meter. Find the extension of the spring. So we have a given mass of 200 kilogram and the spring's constant of 400 Newton per meter. So let's determine the extension, which is the x. So Hooke's law, 2k times x. We only have k, but we don't have, no. We need to determine the extension, but we don't have force, but we have mass. So as usual, force is equals to mass times gravity. We have a 2 kilogram mass times the standard gravity, which is 9.81 meter per second. So 19.62 Newton. So let's substitute. X is equals to force over K. X is equals to force, which is 19.62 Newton over 400 Newton per meter. Cancel. 19.62 divided by 400. So the distance is 0.05 meter.
Good morning, everyone. Today we're going to talk about statically indeterminate problems and thermal stresses. I'm your presenter, Jose Patrick M. Obaob. In engineering mechanics, structures must be analyzed to determine their internal forces and reactions. Some structures can be resolved using only equilibrium equations, while others require additional methods. These are known as statically indeterminate structures, and they are closely related to thermal stresses, which occur due to temperature changes. Statically indeterminate structures. A structure is statically indeterminate when the number of unknowns exceeds the number of equilibrium equations. This means equilibrium equations are not enough. Additionally, equations based on deformation or compatibility are required. Next is degree of indeterminacy. It is defined as degree of indeterminacy equals number of unknowns minus number of equilibrium equations. Some example of this is we have the fixed beam, which is indeterminate, and also a continuous beam, which is also indeterminate. Why indeterminate structures are important? More stable and rigid. Better load distribution, common and real-world structures, just like bridges and buildings. However, more complex to analyze, requires knowledge of material behavior and deformation. Because of its stableness and rigidness, indeterminate structures are important. It also has much more load distribution and also common in real-world structures, for example, bridges and buildings. However, indeterminate structures are more complex to analyze. But in order to analyze those, you need knowledge of material behavior and deformation. Next is we have methods of solving indeterminate structures. First, we have compatibility method, or also called as force method. This removes extra supports and use deformation equations to solve unknowns. If you don't know deformation equations, this is the formula. Fish fillet is equals to P L over A then E. P is your axial load, L is your original length, A is your area, and E is your elasticity. Next is stiffness method, also known as displacement method. This uses displacement as unknowns. So you are looking for displacement. This is much more common in computer analysis. Last is we have the superposition method. This breaks structure into simpler parts, adds results together. Next is we have thermal stresses. Thermal stress is the stress developed in a material when it is subjected to a change in temperature and expansion or contraction is restricted. First, let's have free expansion. If a material is free to expand or it can expand, so we have the formula delta L is equals to alpha L delta T, where A or alpha is equals to coefficient of thermal expansion, L is the original length, and delta T is change in temperature, which means that delta L is the change in length. Next is we have restricted expansion. If expansion is prevented, internal forces develop. This causes thermal stress. So which means a material that cannot expand, which internal forces develop inside of it. This is what you call thermal stress. The formula goes like this. Omega is equals to E alpha delta T, where omega is equals to the thermal stress, E is equals to modulus of elasticity, delta T is the change in temperature. I have here practical examples. First, we have the railway tracks expanding in heat because of the too much friction between the train wheels and the train tracks. Next is we have bridges with expansion joints. Next is a fixed bar between rigid supports. And last, we have pipelines exposed to temperature changes. So, in conclusion, statically indeterminate problems and thermal stresses are essential in engineering analysis. While indeterminate structures provide greater stability, they require more advanced methods to solve. Temperature effects must always be considered as they can significantly influence structural behavior and safety. So always keep in mind the temperature effects when building something because as it said, they can significantly influence structural behavior and safety and may cause harm or can be dangerous. Thank you for listening. Once again, I'm Jose Patrick M. Obaob, and I hope you learned something about statically indeterminate problems and thermal stresses. Thank you.